the best way, since I'm an astrophysicist, I will introduce him thus. A friend of mine, an astrophysicist, was once giving a talk for stringers in Princeton about cosmic rays, whatever, and after the talk he said, you know, Witten is really great, he knows what's a shock wave. So Alex, of course, works on things like creation of the universe, multiverse, inflation, cosmic strings, and yet he knows what is a photosphere, so I'm expecting a really great talk.
Okay. Thank you. This kind introduction. I'm not going to talk about photospheres here. Okay. So in this talk, I'd like to discuss the multiverse scenario that has emerged from the theory of inflation. This scenario tells us that tells us something about regions that we cannot see, regions beyond our cosmic horizon. It says that these regions are very different from what we observe around here, and may even have different constants of nature. And I'm going to discuss how we can test this kind of theory, and if time permits, I'll talk about its implications for the beginning of the universe. This scenario is based on the theory of inflation, and many of you are very well familiar with this theory, but Andrei told me that it would be a good idea to give a brief introduction.
Because some graduate student told me so.
Okay, so this is shifting responsibility.
Exactly.
So I'm going to give a very basic introduction, sticking to kind of concepts, and this is the spirit in which the whole talk is going to proceed. So inflation is a period of very rapid accelerated expansion in the early universe, and it is driven by a high energy false vacuum. Now vacuum is what you get if you remove everything that can be removed. It is just empty space. But of course, for a particle physicist, vacuum is very different from nothing. It is a physical object which has energy and pressure and can be in different energy states, which are referred to as different vacuum. So let me list some relevant properties of this false vacuum. First of all, it has large energy density, which is denoted here by ρ. And this energy density is just a constant of nature. It doesn't change. It's very different from density, say, of a gas. If you increase the volume, the gas gets diluted, not vacuum. So vacuum energy remains constant, and the energy contained in a volume V is simply proportional to the volume. From this, it follows immediately that vacuum has pressure equal to minus ρ V. Right? And this pressure is large, and if ρ V is large, and it also is negative. So it is not like a pressure in a gas which pushes outward, it just pushes inward like a stretched piece of rubber. It's like tension. The most important property of this false vacuum is its gravity. This is a Newtonian limit of Einstein's equations. On the right-hand side, we have ρ plus 3p, and for non-relativistic matter, pressure is always much smaller than the energy density, and we get the usual Poisson equation. But in the case of vacuum, P is equal to minus ρ. This right-hand side changes sign, and this indicates that the gravity of vacuum is repulsive. And this kind of vacuum is called false because it is unstable and it decays into a low energy vacuum like ours, and this excess energy goes to produce a hot fireball of particles and radiation. So this is all we need to know about false vacuum. Alan Booth suggested that early in its history our universe was in the state of false vacuum. Why was it so? It's actually a good question, and maybe I'll have something to say about it at the end of the talk. But let's assume that this was the case, that initially there was at least a small region of the universe filled with false vacuum. Then the repulsive gravity of the false vacuum caused that region to expand very fast. And since false vacuum doesn't get diluted, the expansion rate remained constant for this period, and this means that the universe expanded exponentially. So in a very short time, a little tiny nugget of false vacuum becomes much bigger than the observable presently universe. Then the false vacuum decays, producing this hot plasma of particles and radiation, and this is what we call the Big Bang. And after that, gravity becomes the usual attractive gravity, and the universe expands by inertia. So from that point on, the standard hot Big Bang cosmology takes over.
But in this picture, why there's a reheating isn't explained. From what you've told us so far, what changes? It doesn't just keep exponentially expanding without the phase of
Well, because this false vacuum is being false, it is unstable and it decays. Right? And this excess energy is what produces this heat.
I mean, in the picture you told us so far, that wasn't clear. That has to be added, I guess.
I thought.
Okay. Anyway, fine. It's okay with me. I just meant to say.
It is postulated that false vacuum decays. That's all he needs.
Well, here it was mentioned, but I'm not pretending that I'm proving anything. It's just a brief and hand-waving review of inflation. So this scenario explains some of the puzzling features of the Big Bang that had to be postulated before the theory was introduced. In particular, it explains the homogeneity of the universe, its flatness, that is, the geometry on the largest scales is close to the Euclidean flat geometry. And it also explains the small inhomogeneities on top of that, which arise as quantum fluctuations on top of this smooth background. So when this theory of inflation was introduced, well, maybe let me mention this about the theory of inflation is not a theory in the sense that the standard model of particle physics is a theory. It's not a specific model. It's actually a wide class of models which have this period of inflation in them. So in some models, the false vacuum is this metastable state, and it decays through bubble nucleation, through quantum tunneling, through a barrier. In other models, there is no minimum of energy, and most of the models of inflation include a scalar field, which is, if there are any condensed metaphysicists here, this is what we would call order parameter. So in other models, there is no minimum, but there is a flat maximum, and this little ball, which represents the scalar field, rolls slowly from the top of the potential. And while it rolls, the energy density, the potential energy density, which is, this is a graph of, remains nearly constant. And this is all we need for this state to behave as false vacuum, right? Because the defining property is the constant energy density. And despite the variety, and there are other models that I'm not discussing here, but despite this variety of models, the key predictions of inflation are rather robust. And by now, we have pretty impressive evidence for inflation, that is supporting predictions that the theory has made. The main success of inflation is predicting the spectrum of density fluctuations, which is nearly scale invariant, and the fluctuations are adiabatic. And not only the closeness to scale invariance is confirmed, but also the predicted deviation from scale invariance is in agreement with the simplest models. Also, inflation predicts that the universe should have flat, large-scale geometry, and this has also been confirmed with about 1% accuracy. So by now, inflation has become the leading cosmological paradigm. And since inflation agrees with the data in our observable region, perhaps we should give some credence to what this theory tells us about the regions that we cannot observe. And this is what most of my talk is going to be about. Generically, one finds in an inflating universe, inflation does not end everywhere at once. It ended in our region some 14 billion years ago. That's what we call our Big Bang. But in other regions, it is still continuous. The reason for that is that the end of inflation is triggered by quantum probabilistic processes. And that's why it doesn't end everywhere at once. There is a stochastic element in this theory. And so it is a competition between exponential growth of volume and exponential decay of volume due to this decay of false vacuum. You can think of it by analogy as like multiplication of bacteria, right? So bacteria multiply, but there are antibodies that are killing the bacteria, and whichever process wins, depending on that, either the bacteria die out or they multiply without bound. So here, multiplication should be, at least generically, more efficient because you want inflation to be sufficiently long to make the universe very large, as we observe. So, in this sense, inflation is generically eternal. It's eternal in the sense that it never ends completely. There are always parts of the universe that are still inflating, and actually we can show that the volume of those parts grows exponentially. And they say generically because you can construct models where inflation is finite if you try really hard. But if you write a generic model, it's very likely to be eternal. Okay, so here is it works slightly differently in different models. Here is an example of how it works in models with bubble nucleation. So here, this yellow background is the false vacuum, and you imagine that it expands exponentially in all directions. And bubbles of low energy vacuum pop out spontaneously and immediately start to expand. So if this were happening, this is like a first order phase transition. And if this were happening in the lab, the bubbles would collide and fill the entire space. But here, the bubbles are driven apart by this inflating false vacuum, right? And this opens space for new bubbles to form. And this process continues forever. Okay. So we live in one of these bubbles. And for all practical purposes, this bubble is our self-contained bubble universe. We cannot really travel to other bubbles. Now, in particle physics models, there are typically a number of different vacua, and these vacua are characterized by different values of constants of nature. So here, and then this process of eternal inflation will generate all sorts of bubbles. So there will be bubbles within bubbles within bubbles. And all possible vacua allowed by the theory will be realized in this, what is called multiverse.
But sorry, do you have a right to say particle physics predicts? Because the only confirmed particle physics is the standard model, and that one does not have different
I think prediction and confirmation are two different things. So any given particle physics model makes predictions, right? But
whether or not it was confirmed is irrelevant.
It's relevant, but it's an open question.
But it's really a serious question. So standard model doesn't have different vectors, correct?
Standard model, well,
what do you mean, like different background?
No, but
is there like ideas?
There is some Higgs potential, right?
Yeah.
You can fall into
it
something,
isn't
right?
It isn't a first order phase transition, but of course there is a transition. I mean, it is not true bubble nucleation in the standard model.
Okay, but this picture does not apply to standard model, okay? But even extensions of the standard model would have quite a few vectors, right? So in theories with extra dimensions, this process goes with a vengeance. And the reason for, in string theory, estimates go as high as this 10 to the 500, which is mostly a symbolic number that Lenny Susskind came up with. But the reason is easy to understand. In these models with extra dimensions, there are, you have to curl up the extra dimensions. You don't see them, right? So they have to be curled up to or compactified to a very small size. So you can picture a compactified space like a straw, right? One dimension is long and another is curled up. It is the compactified dimension. Now, if you, instead of one, there is only one way to compactify one dimension. But if you have two extra dimensions, you can compactify them on a sphere, on a donut, on a pretzel with 2 holes, on a pretzel with 3 holes, and so forth. So there are many options. If you have 6 extra dimensions, like in string theory, the number of possible compactifications is combinatorial. So that's where this partially, that's where this large number comes from. Okay, so there is this multiverse string theorists who tell us with an enormous number of different type of low energy physics. Many of them will be similar to ours. Most of them will be very different. I should tell you that this picture is rather controversial, and some prominent physicists say, first of all, they say that this picture is untestable, unfalsifiable, and therefore unscientific. Some other physicists, mainly string theorists, would tell that even the concept of eternal inflation is not consistent with some fundamental principles of quantum gravity. And this list includes our friend here as well. Then some equally, no less at least, prominent physicists are strong believers in the multiverse. For example, Martin Rees at a meeting said that he believes in multiverse so much that he would bet the life of his dog in the multiverse. And then Andre Linde raised the stakes, and he said that he would bet his own life. And then Steven Weinberg said that he believes in multiverse so much that he would bet the lives of both Andre Linde and his dog. But of course, in physics, theory stands or falls depending on the evidence, regardless of how much different people believe in it. So the question is, how can we test these kind of multiverse models? One idea was developed by Matt Kleban and collaborators. If this is our bubble that we live in, if another bubble forms close to it, they will collide. And this may leave an imprint on the microwave background. And these people calculated what this imprint will look like. It will look like a circular region on the microwave sky which has higher or lower intensity of the radiation. However, no convincing pattern like this has been observed, and there is no guarantee that it would be because observed in our horizon, because whether or not it is likely to be observed depends on the rate of bubble inflation, and this is a model-dependent quantity. So this would be a direct test of the multiverse if we found such evidence, but in lieu of that, we have to resort to indirect tests, and that's trying to predict the values of the constants of nature. Different bubbles have different values of the constants of nature, and we can try to predict the values of the constants that we are likely to observe in our region. This leads us in perhaps even more controversial area. So this is a line of reasoning was originated by Brandon Carter, who introduced what he called the anthropic principle. And that says that we can live only in bubbles in which the low energy physics is consistent with the existence of life, which is of course in a way is a trivial statement, but it has some explanatory power because many people observed that if you change the values of the constants that we have in our universe by relatively small amounts, you seem to end up in a universe which is not suitable for life. So for example, you can have no elements other than hydrogen, and that of course is not good for it. You want to have some complex chemistry in order to have life. So, but anyway, as I said, this is this kind of approach does not help you to test the theory, but we can try to turn this into a testable prediction. So how can we do that? So here is the strategy that you can use. So suppose you have a theory of the multiverse, which allows you to calculate what you need. So you assume that there is a theory, right? Then, suppose we're interested in some parameter, x, whatever you want to predict, and you want to calculate from your theory the probability distribution of the value of this parameter, values of this parameter measured by randomly picked observers in the multiverse. So you think of yourself as being randomly picked in the multiverse. Then you typically will get some bell-shaped distribution. You identify the range which corresponds to your desired confidence level, and you say that this is, you predict that this variable x will have a value within this range. So this assumes that you are a typical observer, because there will be some unlucky observers who live at the tails of the distribution, but say 95% of observers who will follow this prescription will make a correct prediction. So this assumption of being typical is what I call the principle of mediocrity. And that's, I think, the best you can do to make predictions in the multiverse. And this approach has been used. And the most, I would say, I would even use the word spectacular prediction, was that of a cosmological constant, which was started by Steven Weinberg and then followed by a number of other people. So let me give a mini introduction in the cosmological constant, because it is a very troublesome parameter. It is plagued by various problems which were with us for many decades. And I would say any theory that can resolve these problems deserves to be looked at carefully. So cosmological constant is the energy density of our vacuum. So suppose you removed everything from this room, everything including photons, nothing is left. Still, electromagnetic field has 0-point oscillations. Those you cannot remove. And the vacuum energy will contribute to vacuum energy, right? So it is just sum of half h omega for each frequency, right? And the sum goes all the way to infinity. Then, of course, this is an infinite sum, but then you can say, okay, when the wavelength becomes over the Planck scale, we don't know what we are doing, so we should cut it off at least at that point. And if you do that, you find that your contribution to lambda from photons is 120 orders of magnitude larger than the average density of matter in the universe. And this, of course, is a ridiculously large number. Observationally, the vacuum energy density is about twice the average matter density. And so the disagreement between observations and this prediction is crying for an explanation. Sometimes it was called the worst prediction in theoretical physics. No, so there is a question of why the observed lambda is so small, which is called the cosmological constant problem. As I said, it was with us for almost a century. And best minds in theoretical physics tried to solve this problem with very little success. People noticed, of course, that fermions and bosons contribute to vacuum energy with opposite signs. So in principle, you can have a cancellation. But what you need here is cancellation up to 100 million decimal point, which is a bit too much to ask for. So this is the cosmological constant problem. Then there is another problem. Notice that the observed value of lambda is pretty close to the average matter density in the universe. Why is that? This is rather puzzling for the following reason. So, as I said, this vacuum energy density remains constant in time. It doesn't change. But the density of matter does not. Right? So the density of matter was much larger at earlier times. Sorry. At earlier times, and it will be much lower at later times. So we seem to be living at some very special epoch in the history of the universe when these two densities are comparable. And this is called the coincidence problem. Why is that? Why is this coincidence? Okay, so let's see how the multiverse can help us with these problems. If we have this multiverse with different bubbles having, let us focus on cosmological constant. Since we have 10 to the 500 vacua, we can select bubbles where other constants of nature are pretty close to what we have here, and only the cosmological constant is substantially different. Then lambda will take values in these different bubbles in this range, this huge range. Yeah? And then when matter density at early times in each bubble is high, you can have some structure formation, like density fluctuations will grow. But when lambda starts dominating, when raw matter drops below lambda, lambda has repulsive gravity, all structure formation stops. So if lambda is large enough, this will happen before any galaxies had a chance to form. So Weinberg estimated the range of lambda in which you can hope to observe any galaxies to speak of, and lambda has to be less than 1,000 times the raw matter. Okay, but now we want to do better, because this is anthropic range. We don't, obviously there are no galaxies, there are no observers, but now let's try this approach that I mentioned. Let's try to find the probability distribution for a randomly picked observer. So I can represent this distribution as a product of two factors. First, the volume factor. It is just a fraction of volume in bubbles with a given value of length. And then this calculation of this should be based on particle physics, because what are the allowed values by particle physics, and also on the theory of inflation, on transition rates between different bubbles and so forth. And then the selection factor, which is the number of observers per unit volume. Right? So fraction of volume times the number of observers per unit volume gives you the number of observers. Now, of course, if you look at it at first sight, you would say we have no idea how to calculate either of these factors. We don't understand string theory or any other fundamental theory well enough. Calculate the first, and we have no idea how to count observers. But some progress can be made here. starting with this volume factor, we notice that the anthropic range that Weinberg indicated with lambda less than, say, 1,000 times the meta density is tiny compared to the full range of variation of this factor. It varies between minus Planck energy density to plus Planck energy density, and this is 100 orders of magnitude, and here we are talking about only 3 orders of magnitude. So in this situation, it's likely that any distribution, as long as it is roughly smooth, will look like a constant in this tiny range. Right? So it seems plausible to assume that in the relevant range of lambda, this volume distribution can be approximated as a constant. And then so please protest if you don't agree with what I'm trying to say. Then the selection factor, you need to know the number of observers per unit volume. And I suggest that it is proportional, roughly, to the fraction of matter that clustered into galaxies. The idea being that you have matter clustered into galaxies, then you have some number of stars per galaxy and some number of observers per star, but neither the star formation process nor observer evolution are in no way influenced by the value of lambda. Right? So those factors will drop out here. They will be independent of lambda. The only thing that does depend on lambda will be the number of galaxies, which is the same the fraction of matter clustered into galaxies. I say roughly because, of course, I'm assuming implicitly that I'm talking about galaxies of some more or less specific size. But we can talk about the subtleties, but let's take this rough model. We have galaxies, say of size like ours, and then the number of stars per galaxy will be independent of lambda, and the number of observers per star on average will also be independent. So if you make these assumptions, this is the distribution that you get. And this is the observed value. So you see it is well within the 2 sigma range of the distribution. The distribution drops sharply down here, simply because if you go to larger values of lambda, you have too few galaxies, right, because of this gravitational repulsion. And the distribution drops at small values of lambda simply because of the phase space factor. So this range is so small that the probability to be there is small proportionally. So, and notice also that so this approach explains why lambda is small. It predicts, actually, I should say that these calculations were done before the cosmological constant was observed. So it was a genuine prediction. It was not an explanation of the fact. It also explains the coincidence question, simply because it tells you that if you increase lambda more, no galaxies will be formed, right? Or very much fewer galaxies. Basically, what this predicted range is, it tells you the peak of the distribution is such that you allow all galaxy formation to occur, and then lambda starts to emerge, not before, right? And we live not very far from the galaxy formation network, right? Galaxy formation occurs in order 2-3. So the fact that we live close to that epoch is just a statement of the fact that we live close to the epoch of galaxy formation. Now, another important fact is that there are no viable alternative explanations for either of these facts of smallness of lambda or
I don't understand any of this. Suppose I'm in 1987. I know that lambda is less than about 10, simply otherwise it would contradict direct observation of data. And then I just say, since there is no reason to believe that lambda is 0, my prediction that it is less than 10, spectacular success 13 years later.
Well,
why did you need to tell us this lengthy story? What does it add to my naive thinking?
Well, first of all, it adds, most people believe that lambda is strictly incomputable, because they thought that if lambda is so small, it should be equal to 0 because of some symmetry.
Because Landau wrote this in his textbook.
Because who?
Landau and Lifshitz.
Yeah, I don't know. I didn't know that they wrote it, but many people like take so what's the name of the particle string theorist who died several years ago? Polchinski. Yes. So Polchinski, when this prediction was made, he said, okay, if that's going to happen, I will quit physics. He didn't, fortunately, but people didn't believe in this at all. And also, if you discuss just based on entropic considerations, this would give you an extra order of magnitude, and that is it will be more probable within that next order of magnitude than where we find ourselves. So I don't see what. Do you agree that the small values of lambda at least?
I will never understand it, so never mind.
Well, I will work on it. All right.
So, but this seems then to forbid the possibility of the negative just to choose
right. This is plotted only for positive lambda. Negative lambdas behave rather differently from positive lambda, and you can do the calculation, and you find pretty similar results. So it is.
But still, I mean, we just choose the what we can claim is just absolute value of lambda is smaller than rho n. But it's not.
No, for negative lambdas are more restrictive actually, because if you look at Weinberg's range, right, it's 1,000 here and it's only 20 here.
Can I say something? So each of us is one of those colored circles, no? So our observer horizon, I mean,
Each of us, you mean?
our universe, what we see.
Our universe is just one of these.
One of the balls. But I mean, then if there's a theory for the whole multiverse, then all those universes are entangled with each other. Can we, if we, right? I mean, because the degrees of freedom, I mean, the degrees of freedom can be entangled, even though they can be very far apart. So is it possible to basically kind of say, well, in my universe, I have absolute no knowledge of what happens outside my observer horizon, but somehow I should have some, not access to the information, but I live kind of on a state, on a role, which is not a pure thing. And then I have a probability distribution of having some energies. If we study kind of the average energy on our side, can we get a curve like this? Similar to, for example, easy thing. I have Minkowski and Rindler. If I live in Rindler, I don't see an observer that is in pure vacuum. I see a sum of infinite states, right? Because the vacuum in Minkowski is not vacuum in Unruh. So in our own universe, can it happen that we can define a probability distribution function for the lambda, given that we are entangled with the rest of the stuff? Can we have a rho that is the thing that describes us, but in the end has some information of what is outside us?
So you're saying that by doing some quantum measurements,
well, yes,
in our region we can learn something about some other regions. Maybe, but if you have a first order phase transitions, you also have bubbles, right? And there you don't expect one bubble to contain information about the other. Maybe here it is different, but at least I don't know that there is any convincing theory that predicts that. That's a possibility.
but I should think, I don't know too much, but I should think that the entire square with all the circles and the green thing is one local theory of nature. Can I think that that's a true theory of nature, and I decided to trace over degrees of freedom in my little circle? Is that what I should see from the picture?
I'm not saying you should, but this is a naive, maybe, point of view that people who talk about the multiverse usually take. These bubble nucleation events are independent quantum events. And they do not, the bubbles do not really have any substantial entanglement. At least that would allow you to learn something about these other bubbles. Okay, maybe there may be something in there. So I told you that at least in my view, this prediction of the cosmological constant is our first evidence for the multiverse. Andrei will disagree, but let me tell you about the problems of this picture. The main problem now, and it is also a problem of inflationary cosmology in general, it is the so-called measure problem. So if you want to predict any outcome of any measurement, right, you have to deal with the fact that, and think of yourself as a randomly picked observer, you have to deal with the fact that the number of observers who would do such a measurement in the multiverse will be infinite. And as time goes on, this multiverse expands exponentially, and we have more and more galaxies form, more and more observers. And so to compare probabilities of different outcomes of your measurement, you will have to compare infinities. Now, usually you deal with this problem by introducing a cutoff and then moving the cutoff to infinity. For example, you can count all the measurements made up to a certain time, compare the probabilities of result, and then take the limit when this time goes to infinity. And this you can do and get results. The problem is that the result depends on the choice of time variable that you use. You can use the time measured by the clocks of the observers, or you can use time measured, say, by the expansion factor of the universe, by how much the universe expanded after that. And the results are rather different for some choices, for some parameters. Not for cosmological constant, in this case it is not sensitive, but other parameters that you can try to predict give rather different results. And that, of course, is an embarrassment. So there's a measure problem in the sense of probability measure problem. And here we really may need some new ideas. Various things have been suggested, but I think it is fair to say that at this time the problem is unresolved. So if someone is looking for a difficult problem, this is, I would suggest, to try that.
But don't you have a cosmic time, like you have cosmic time now in post-Big Bang universe?
Sure, this is what I call the time measured by the clocks or observers. Yeah, standard cosmic time, or instead you can say, okay, let's measure, use the clock that measures by how much the universe has expanded.
What do you mean? How much it has expanded? If you have a co-moving observer, he just measures the rate of expansion. This gives you the expansion factor, right? So, we are talking about different normalizations, so to speak.
I say that you start your observers at some, suppose all your observers start at a certain time, they set their clocks. Then they can either look at their clock and say, okay, this is time. Or else they will wait until in their location the universe expanded, say, by a factor of 100 from the moment when they started.
Yes, basically I'm saying why time, why not the total expansion or something?
Yeah.
Okay.
So
Since
they
we
all
don't know
time,
what we are talking
in
about.
general relativity there is no preferred choice of time, right? Time varies. Okay, so I think I will not have time to get into that, but maybe let me briefly tell you about the beginning of the universe, because I promised to Andre that I will talk about that. So we have this eternally expanding multiverse, right, with new bubbles continuously formed. And a natural question that arises is whether or not you need a beginning for this picture. Could it be that the universe has always been like that, right? Without beginning and end, eternally expanding universe. The answer is that it's not possible, and this is due to this theorem that I proved with Arvind Borde and Alan Wood. The theorem says that the universe that is on average expanding is geodesically incomplete to the past. Geodesically incomplete means that there are geodesic lines in the space-time that cannot be continued to past infinity. And that means that you don't have the whole history, right? So there's some boundary in your space-time. So this is a mathematical theorem, you cannot argue with that. Also, it's quite general, it doesn't assume Einstein's equation, it's a kinematic, it's a geometric statement.
Sorry, can I interrupt? Does it follow immediately that something more radical, that inflation is necessary, like creation or bounds? Is it a direct, this statement, is it a direct consequence of this BGV theorem?
Well, under the conditions of the theorem, the universe is on average expanding. So if you have a contracting universe, the theorem doesn't tell anything about it. But if the universe, or if the universe contracted from infinite size and bounds started expanding, that's okay. But
So either bounds or creation, correct?
Correct.
So you do agree that this radical statement is a direct consequence of BGV?
Yeah. Theologians are very excited about this.
Theologians. But shouldn't we be too?
I am. Well,
You just said that in the past you need have a theory of quantum gravity to understand where it came from.
sorry?
It just, when you say that it's geodentically incomplete to the past,
Yeah.
it's, what I'm saying is that theologists should not really be happy about this. All this is saying is that we need a theory of quantum gravity to understand, to evolve all the way to the past.
Yes.
That's it.
Right. But I think I would say that it implies that the universe has a beginning, because a beginning and time are semi-classical concepts. Right? So if you go back in time and you come to a point where the concept of time and beginning no longer apply, okay, you use quantum gravity there, but I would say that's the beginning of classical evolution. So anyway, and then the question is what happened before inflation. So inflation cannot be eternal. The question is what happened before, and even before I start answering this question, you can ask, and what happened before that?
When you say universe, do you mean the sub-universe or somehow the whole thing in your picture?
The whole thing. So the answer that, or the approach that addresses this issue of infinite regress, of where everything came from, is the possibility that the universe was spontaneously nucleated out of nothing. Where by nothing, I mean not the philosophical nothing, but a state with no classical space and time. And this, I will take another minute or two, is that okay?
I'm not the boss, Yifan is the boss.
That's fine.
Okay, so of course, since Lucretius, we are told that nothing can be created from nothing, maybe even before. But if you ask physicists, it is because of conservation laws. Right? Matter has positive energy, and therefore you cannot create matter if there was none before. But it is a mathematical fact that the energy of a closed universe is zero. The energy of matter is exactly cancelled by the negative energy of gravity. Also, electric charge of a closed universe must be zero. If you think of a closed universe, you put a charge on the North Pole, the lines of force go like that, and they meet on the South Pole, creating a charge of opposite sign. So charge of a closed universe must be equal to zero. And so it seems that all conserved quantities in a closed universe are equal to zero, and there is nothing to prevent it from being spontaneously created from nothing. And there is a, if you address this problem in the framework of quantum gravity, you can find the mathematical description of this process of the creation of the universe. And it has been discussed by this group of people and then by many afterwards. Again, all topics I talked about today are controversial, and this is not an exception. Here there are the two main approaches. One, to quantum nucleation of the universe, give similar results. The probability of nucleation is e to the plus or minus s, but the sign obviously is important. So, okay, so anyway, I will not read the summary. I'll stop here.
Could you talk about I don't know what's the proper name of it, but I associate it with Paul Steinhardt. I don't know what the present correct name is, but with kind of collapsing universes instead of expanding ones. And
Ekpyrosis.
well, that was the first one, but it
Oh,
has,
there is a new one
I
now?
think so, but I don't know the name of the new one. So I'll call it ekpyrotic climb. Anyhow, can you comment on how that picture
Yeah,
fits with this?
so, let's see. Yeah, I had discussion with Paul about it, but now I don't remember really the details. But the point is that in the early ekpyrotic theory, they have contracting universe from an infinite size, then bouncing and re-expanding. I have no problem with that as far as this theorem is concerned, but
it seems like it contradicts what you were saying, that there has to have been at least in the way they characterize it, you say the third point, it's eternal for future, but it's got to have a beginning.
yeah, because if you think of this physics with bubbles nucleating, right? If you allow bubbles to nucleate in the contracting part, of course they will fill the universe immediately. So this contracting part has to have some totally different physics. Also, the bounce itself in these models like ekpyrosis, it has never been described physically, right? So they say, okay, there should be some process that allows the universe to bounce.
Presumably they would say that about the nucleation of your bubble.
No, nucleation of the bubble is, if you write the simple-minded Schrödinger equation for a closed universe, you find that there is a barrier. Closed universe filled with cosmological constants. Then you find that there is a zero size, right? This is the size of the universe, and this is the potential in the Schrödinger equation. And the potential has this form. So you start with zero size, and you can tunnel, and this size corresponds to one horizon of the system, right? At this semi-classical level, it is a perfectly valid description of quantum nucleation.
Are the bounce scenarios of Steinhardt and friends, are they fine-tuned in any way, or because if you can say that they're fine-tuned, they don't fit in the context of your theorem, which is about sort of an average.
Well, you know, I do not pretend to be an expert on Paul's scenario, but to me, an infinite contracting universe is not a very attractive starting point, right? Where did that come from?
But at least it is geodesically complete in both directions.
Absolutely.
Right? So it's okay. You don't need no creation. It existed forever and it will exist forever. Everybody's happy.
Well, but there is an abracadabra in the middle.
Yeah, there is a bounce.
How do you know the geodesics?
Right. I
You
agree.
don't know.
Yeah. The missing point is the bounce, right? Nobody knows how to
It's
do
the crucial point.
I agree. Yeah, who knows what's worse, creation or
Right.
bounce? Yeah. Do you agree?
I agree, but do you think the universe started being infinite and contracting? Who fine-tuned this
Well, I
contraction?
think they argue it never started. It was just always doing it, whatever, however difficult that is for us to imagine.
I don't know how always. I mean, now we live in an expanding.
No, I think they say we're living in a contracting.
No, contraction
like-
was their replacement for inflation.
Oh, you're right. But now that we're got a cosmological constant.
Okay, well,
right,
look,
right. We should talk about what you want to talk about, not these other stuff.
no, I would happily talk
No,
about
now
it
it's
if I
questions.
understood it
We can
better.
talk about what we want. So can you tell us, does it go anywhere? Like, for example, obviously it's hard to avoid thinking about this, right? Since inflation is geodetically incomplete, one wants to think about it, but you have just demonstrated that there was no progress in this field since 2003. Right, because 2003 was the latest reference on your slide.
No, I mostly gave references to the earliest paper, not to the latest.
Or people keep writing. Okay, they just don't deserve the citations.
No, absolutely, they deserve.
His page will be full of citations.
But I think that earlier people have maybe deserved it a little more.
Oh, the latest was Kleban, probably, right?
No, Kleban was the first to study the bubble collisions.
Which was later than 2003, right?
Yeah, it was 2008 on the side.
Okay.
Okay, here I didn't know.
I came late, sorry.
So where does it go? I mean, is there? Do you have any idea? Like,
well, I can tell you one place where it went. I went to a conference in Tbilisi, Georgia, and Gia was there. So as I mentioned, Gia doesn't like the general inflation because he doesn't believe in de Sitter space. He doesn't believe that
I'm sorry. Why are you constantly using the word believe? Right? Isn't it the very definition of physics? Is that I don't care what you believe, right? I care only what you can prove.
Well, you know, if you say that something is not consistent with basic principles of quantum gravity, I think we're here entering the area of belief. Because quantum gravity is not really a very solid theory in which you can really, make statements very confidently. Anyway, what I was going to say is that when I was talking to Gia, he suggested that maybe our points of view can be reconciled. That suppose eternal inflation is impossible, as he
Believes.
Yeah. Then vacuum energy can only be 0 or negative, right? But Dia suggests that we can still have a multiverse through this quantum nucleation, right? So suppose you have different, string theory gives you a landscape of possible vacua, but now you don't have bubble transitions between them, you don't have eternal inflation, but you have nucleation of universes with these fields with these different vacua, and all these universes, each of them will have a finite number of observers. Right? For example, negative lambda universe will collapse after a finite time. So then you don't have a measure problem, for one thing, right? The number of observers is finite. You don't need to introduce any cutoffs, and if you believe that omega observationally is positive, this is your chance of having positive omega within a maybe reasonable theory. So anyway, we started discussing this here. But you ask where it is going. This is one place where it might go. You can have a multiverse based on quantum cosmology. Right? You can calculate the probability distribution like this, and this first term would be bubble nucleation, which we need to calculate.
How is this consistent with dark energy?
Quintessence.
So the nucleate universe that has negative CC, but there's also some quintessence.
Yeah, like if you have 0 CC, you can have something like this. A negative will go down, but still you may have some time span for us to enjoy. So you wanted to?
I was just I'm puzzled by this single inflator. Do you have any good reason to just have one scalar field? But doesn't it worry people that we just out of the blue have a single scalar field? Why not 100 scalar field?
Well, I mean, did I say there should be necessarily single input? Or,
This is so much not a theory, but a picture that you can replace one scalar field with 10 vector fields. It will not change a single.
No, but it will.
Am I
change.
right?
No, it will change some even qualitative features of the scenario. But people studied that. There are so many people working on inflation, you know. So.
But doesn't it bother you, this thing, that you don't really know what you're talking about?
So which part of what I don't know?
Like how many fields, whatever, arbitrary potentials.
Look, it's if you
So
think
some
of it,
people call you promoter of the multiverse.
promoter.
Right. So does it bother you, or you think it is still?
You know, I would prefer if it were more definite, but I think there are some successes one can point to, and you know, if you the problem with just like the measure problem, the problem with measure problem is not that we don't have a good measure. We have too many good measures, right? And we just don't know which one of them is it. If you think of particle physics, in particle physics, we have one really, really good theory. However, is this the only theory that fits the data? You can write an infinite number of theories that will fit the data. The number, how do you select the group, right, that is based on? I think the state of the art is what it is. So I told you about good and bad, and many people feel aversion to it, and that's fine with me.
I have two questions. One is, it's almost like you're characterizing quantum cosmology multiverse is different from what you were thinking of or speaking of, and so I'd like you to comment and clarify that. And then maybe related is, you might have thought you could examine the general philosophy of multiverse by looking at other parameters besides the cosmological concept that look fine-tuned, like CP or the neutron electric dipole moment story. And some parameters seem nicely explained by the sort of anthropic point of view. I mean, this is, after all, the calculations of lambda were anthropic, basically, even.
Yes.
And but others like the axion seem really look like they're fine-tuned. So I just want you to comment. It seems a little weird to imagine a theory where some things we decide to accept, like what about the peculiar range of masses and mixing angles of things that don't matter to humankind and so on.
Yeah, so let me start with the second question because I already forgot the first one. But,
as a question, is are you making a distinction between quantum cosmology and not?
Yeah, so the second question, here are some other parameters that people looked at. This is what is neutrino masses, and there the approach was used similar to lambda. If you vary the neutrino masses without getting to very large range, but suppose you vary them around from between 0 and 10 eV, right? Then if you increase the neutrino mass, the amount of matter cluster in galaxies decreases. Okay, so larger neutrino masses in this range will have very too few galaxies. And this range, again, you have maybe the neutrino masses are small, not because of seesaw mechanism, but because of this anthropic selection.
Well, it wouldn't hurt humankind for it to be smaller. It just you're putting on this argument. You did it also for the total constant that somehow it would be too fine-tuned if you made it smaller. But that seems really hard to defend. Why that would be 0.1 instead of 0.0001. I mean, too fine-tuned requires some sort of mass scale to compare to, doesn't it?
No, it is probability density. So it basically you can just write your probability on logarithmic scale.
Maybe the question is about the prior of the masses. It's the flat prior.
Yeah. In the case of cosmological constant, because it is a sum of positive and negative values, pretty randomly, so it should be flat.
Sorry, should we thank Alex, and then whoever is interested, we can just stay here and touch it with
Okay,
So you're answering about priors for the
no, but wait, here I think Vanis asked about axions. These guys, Tegmark and friends, they use also pretty similar arguments for axions, but they combine galaxy formation with other factors. They kind of, and they also found the peak at observed value. So if the dark matter turns out to be axion, then
a larger. Oh, you mean the QCD axion, or? But right now there's a huge range of axion mass possibilities.
not necessarily QCD axion.
No, you can't say there's an observed value of the axion mass right now.
No.
Oh, the axion dark matter density.
Dark matter density is
okay.
keeping it of Yeah, and your first question was about the difference. See, if you have eternal inflation, then quantum cosmology is pretty useless. If you create a universe spontaneously, filled with one vacuum, then from that vacuum will tunnel to all other vacuum, and you will fill the entire multiverse. So each entry in the quantum cosmology multiverse will be pretty much identical in the long run. And this idea that Gia suggested I found interesting, only because here you don't have eternal inflation, but you have a multiverse of just quantum cosmology without eternal inflation, and it seems that it has some very different qualitative features than the other one, the multiverse of eternal inflation. So I thought it's worth exploring, but yeah.
One main question. So the values that we observe in our universe kind of are at the peak of these curves. So that means that are the more normal ones. I mean the ones that maximize the probability distribution. That might mean that in the other universe that is not ours, the values of the fundamental constants are like that as well. Because that is very likely. So in all the little bubbles, the constants of the universe are pretty much as well the same number.
This is supposed to be the probability distribution of sum of neutrino masses over the entire multiverse. So if you pick some bubble in the multiverse with other constants of nature similar to ours, the prediction is this is where the neutrino masses will be.
Why should it be observers like us? That seems bizarre. It's one thing if you say, okay, it's anthropic, we know we exist, now we sort of work out the consequences. But if you want to start talking about the whole shebang, then to sort of select your observers to have galaxies, you're terribly skewing the distribution.
Well, I'm looking at the subset, right? At the subset.
Okay.
And again, it doesn't need no observers. We know that the upper bound today is 1 electron volt from observations. And then he's just saying, why should it be much smaller than that, period? No multiverse.
So the argument that it's not a lot bigger than that had to do with.
No, you don't need an argument that it is a lot bigger than that, because it is direct measurement. If it was bigger than that, we wouldn't observe the universe. What is the current upper bound from and left? It's probably like
But that's,
one point.
Upper bound.
but you're
Point
talking about
five of it.
distribution in all in all universes.
But who cares about all universe? I live in my universe, and my universe it is less than 0.5 from direct measurements from BBM,
Less than 0.1.
right? So I don't care about any of this.
Okay, I would tell you that regarding cosmological constant, these predictions kind of evolved with time, but they were started when our knowledge and our bounds of the cosmological constants were pretty
Certainly less than 1,000.
less than 1,000. That's
So-
right, but certainly, but I guess more than 100.
But I think in the 80s, people knew something was wrong, but there either had to be cosmological constant or another universe. That
Well,
way-
in the 80s, I think if you asked astronomers, they all believed that the universe is open.
Right.
So they
Because
wouldn't
knew that-
hear about Alan's,
Okay,
you know,
yeah,
inflation.
but they knew that you needed one or the other.
Yes.
So to some extent, yes, it's a prediction, but it's clear that there's something missing.
Okay, but you know, when something is missing, you don't know what it is. Maybe something we haven't thought of.
Yes, sorry, I have a right now question. Following Andrew's question. So following this logic, so what's the difference between entropic and experimental constraint? Can we say, okay, we don't find the wind because we are just we are giving the similarities to find the wind, but not this.
So
I mean, what's the, because here it's the, you say our neutral mass just taking this peak, right? Which is wrong when you, because higher value is just excluded. Otherwise, we'll live in the universe which heavy neutrino will ruin our universe. So can I say you don't find the wind because we just
you don't find what?
wind.
Yeah.
Yeah, just because we live in a universe we cannot find wind, but it's not because it's external.
Well, the idea would be you'd have to make some argument as to why having a heavy wind would interfere with our universe.
Yeah. I mean, just because otherwise it's infected by us. We can. I mean, I'm just following logic.
Well, you know,
I'm saying it contradicts anthropic principle. By anthropic principle, we should have found WIMP already.
Why?
Yeah. I mean,
Because there is no reason not to.
That's not the
you are trying to mimic the logic I follow.
Exactly.
yes.
No, but isn't it a serious question? Does not the current bounds on WIMP, don't they already kind of contradict anthropic principle?
I don't see why they would.
It would. We know that we must have dark matter. WIMP is a perfect candidate by anthropic principle. The cross-section should have been such that it would have been a thermal relic.
Only
And
if there
yet-
were no other equally good candidates.
Exactly. That's the problem, of course.
Well, you see, the problem, if you try to say that something
If it
like,
does not exist, you invent another explanation. If
So-
it does exist, it confirms anthropic principle.
I think regarding cosmological constant, many bright people tried to find another explanation. Okay,
You again appeal to
None of them-
authority. We don't accept this argument. There is no authority.
okay, equally bright and dumb people.
Isabel is the one who asked the question, I think.
Well, it's more like I don't know, I feel like all of these arguments, anthropic arguments for the neutrino mass or the CC or, similar arguments for the electroweak scale, you always draw this plot where, you draw some probability density varying some parameter, holding everything else fixed. Where, I mean, we know that's not the situation, right? Like, this is a theory with many parameters, and unless you show me a probability distribution in some, high-dimensional parameter space that peaks at the values we see, that is not a, that is not something.
I have two answers to this. First of all, I would defend the point of view that it's justified to restrict the parameter space to just one value.
But if I vary various things at the same time, I mean, if I vary
But maybe, okay,
CC
maybe
as well
let's
as
postpone that.
lambda electromagnetism, maybe I can form galaxies for different values of lambda. It's not, it really, I mean, it changes the
No,
conclusion.
I'm
right?
not telling you that there are no observers who are totally different from us and based on totally different physics. There may well be. But what I'm saying is that if you have this huge multiverse, you can select a subset of bubbles in which physics, low energy physics, is close to ours, except for lambda, for example. Is anything wrong with selecting this? Okay, then I ask, within this set, what is the probability distribution? Okay, I think it is a legitimate question. But if you want to see a multi-parameter distribution, I think the most multi-parameter one was done by these guys. And they looked at lambda and neutrino masses, I think, and dark matter density. So they varied all of that and amplitude of density fluctuations. And they found the peak pretty much where you want it to be, right? Consistent with the data. So
for the density of dark matter, they presumably can't say anything further about axion.
no, they assume that the axion is the dark matter. If axion is a whim, then their analysis doesn't apply. Because if
dark
you
matter
have,
is a whim.
see, if you have an axion, then the prior distribution is easy to find. Axion is just defined on a circle, and it's tilted very little compared to scale of inflation, so the distribution is uniform in the shape.
Oh, okay.
It's pretty clean.
I see. So they needed to be discussing
Yes.
axions. But you could have also just said if the dark matter density were very different, we couldn't form galaxies.
Well, that also, I think, comes into play, but that's a qualitative statement, and the calculation probabilities, right? So
Can I write a Lagrangian for this? I am very I need a Lagrangian. Can I write a Lagrangian for a theory with now, like my bubble and your bubble, and do local physics in each bubble? Can I write something?
you can write something, but you don't know what to write.
Well, so then I cannot write it. See, I don't know what to write. But I mean, is there like a standard basic Lagrangian for a multiverse theory? Like something I can
V
do.
of phi, what do you want? V of phi with a few minima.
Yeah, but in general, but you would say that phi lives in a de Sitter or something similar to de Sitter in inflation, but it's your de Sitter. You're not talking about other de Sitters.
But you cannot write a Lagrangian for model with 10 to the 500 mean. But you can write a simple model, this is what we usually do in physics. For example, people looked at 6-dimensional models, right? With 2 dimensions compactified. It's a pretty rich model with a multiverse with different topologies, different bubbles. You can find nucleation rates, transitions. So you can do all of that. And, of course, you don't want to claim it as realistic.
No, but another question is, why do we choose the neutrino without neutral mass to have the harmonic probability distribution? Because it seems, for example, let's say a seesaw mechanism is inverse proportional to the mass scale. If we say it has the uniform probability on the mass scale, then it has the non-uniform probability on the neutral mass.
Well, I don't remember this paper very well. We discussed different options for prior probability, and I remember that some of these options gave totally crazy results and gross disagreement with what we see. And I think 1 or 2 were acceptable. But I would agree with you, there is no very good justification for choosing prior. In that regard, cosmological constant and axion are different because the motivation to this choice of prior is also.
Because I think this question always also applies to like much more broader like argument perspective of the model building, right? Because sometimes people say, okay, we have a very fine-tuned way of like the gauge coupling, but if we say the gauge coupling comes from the large extra dimension, and then actually if we say the probability of the extra dimension is constant, and then actually the extremely small gauge coupling is even the larger, much larger probability than the large gauge coupling.
Well, you see, all these examples, cosmological constants, neutrino masses, axions, they have the same one feature in common, which is these particles very weakly interact, or these parameters very weakly interact with the standard model, right? And therefore, if you vary, say, neutrino masses, you know that this will not affect, say, the evolution of life. So the number of observers per star will probably be not affected. So if you start varying parameters that affect chemistry, then you certainly not know what's going on.
Yes, sorry. My question is like this. I mean, it's just still based on like the prior of the physical parameter, right? Because it just seems we don't have the clear definition of the priors. So it seems in some case we say magnitude mass is fine. In other case we use the seesaw mechanism for the prior of the magnitude.
Well, you see, I think the word prior, although it is used by people working on this kind of stuff, it's not an accurate term, because right here is a volume distribution. Right? Basically, what we call prior is the fraction of volume occupied by different values of lambda, or whatever parameter you are interested in. But this is a calculable quantity. It is not probability theory prior, where some philosophical definition, and basically there is no good way to define it.
I mean, sorry, I'm just wondering whether the seesaw skill is the skill of the seesaw mechanism.
Where is what?
I mean, when you seesaw mechanism, the skill of the seesaw mechanism is calculable. I mean, the prior of the seesaw, that skill.
No, seesaw mechanism is fine. You don't need any anthropic input to the seesaw mechanism.
Yeah, but then we don't have the well-defined form.
Right, but it is one or the other. We don't know what it is. So maybe neutrino masses are small because of seesaw mechanism, or maybe they are small for anthropic reasons.
Can you remind me on the neutrino plot for the very high masses, like above 10 eV? Why is causing the probability distribution to be suppressed?
Well, because what you assume is that you know the dark matter density, right? So some of this dark matter may be in neutrinos,
right?
Okay, but whatever part you put in neutrinos, it's not very effective at structure formation, because at the time of galaxy formation, the neutrinos are still pretty fast moving, and they do not cluster.
Thank you very much.
Okay, thank you. That's
interesting
group.
Very nice. Thank you.